Hi guys. Alright, so in this video we're going to go over some sample calculations for the heat convection lab. The heat convection. Okay. Alright, so let's see. In this problem we have air. We have air. This is air flowing over a cylinder. And we're providing power to the cylinder somehow. So something like that, providing power. Okay. And in this one, we want to find Q convection, and we want to find the Nusselt number. Okay, so these are the two things we're looking for. All right, now let's see what they give us. They give us the diameter. Diameter is equal to 0.01 meters. And we have the length, which is 0.07 meters. And we have a velocity of 2.5 meters per second. Okay. Alright, I think that's all we have. Now I went to the lab and I conducted this experiment, and these are the data points I have. So I had a voltage of 12 volts, had a current of 2.04 amps, and we had two temperature readings, a T9 which was 26 degrees Celsius, and T10, which is 158 degrees Celsius. Now, 26 degrees Celsius, that's room temperature. So this is, let's say, somewhere around here. This would be T9. And T10 is on the surface of our cylinder. So let's say something like that would be T10. All right, and obviously T10 is the one getting power, so this is a lot hotter than room temperature. Okay, that makes sense. All right, now how are we going to get our Q convection and our Nusselt number? Okay, so for that, we are going to use some formulas, which I have right here. All right, so we have this Nusselt number formula, which is equal to HT on K. We're going to use that later. And this really, really long mess. Okay, so that's one of the formulas we have for Nusselt number. And we have another one over here, which is a little simpler. So here they give us 4 different options. We're going to use the one for the circle because we're dealing with a cylinder. We need to find the range of Reynolds number. We need to find the Reynolds number and then look at one of these ranges. And then if it falls between one of these ranges, then we can use one of these equations to find our Nusselt number. So we can either use this equation or this equation. They should both give you the same answer. All right, so let's go ahead and get started on that. All right, now the first thing I want to do is find my Reynolds number. So I'm going to clear all this. Okay, so we want our Reynolds number. So Reynolds number for a cylinder is equal to the velocity times the diameter over kinematic viscosity. Okay, now we need kinematic viscosity. How are we going to get that? Well, first, we need to find our temperature, because we are going to be looking for this kinematic viscosity and some other properties in our air tables. But in order to look it up on the air tables, we need a temperature. But which one do we use? We had one at room temperature at 26 degrees, and we had one at the surface of the cylinder at 158 degrees. Now, in fact, we're not going to use either one of them. Over here in one of our formulas, we see that we have to use the film temperature. And the film temperature is just 1/2 the temperature of the environment plus the temperature of the surface. So let's go ahead and do that and get our film temperature. All right, so TF is equal to 1/2 T infinity plus TS. And this is 1/2. T infinity is 26 degrees. T to the surface is 158. And from this, I get TF equals 92 degrees Celsius. 92 degrees Celsius. Okay. Now that we have our film temperature, we can go to the air tables. So from table, we get a kinematic viscosity of, here we go, 2.22 times 10 to the minus 5. Now I want to point out that on the air tables, it goes by 10 degree increments, and our temperature was not a nice even number. Oh, not divisible by 10. So I had to interpolate this value. Now I'm not going to go over that in this video. We've taken thermal fluids by now. We've taken thermodynamics. We've done plenty of interpolation. So I'm just going to give you the interpolated value, which is this right here. Okay. So we have our kinematic viscosity. Now we're going to plug that in here, because we have our velocity and we have our diameter, and we're going to get our Reynolds number. So let's do that. A cylinder is equal to, so this is 2.5 meters per second times our diameter, which is 0.01 meters. All this is divided by our kinematic viscosity, 2.22 times 10 to the minus 5, and I forgot to put this is meters squared per second, and this is meters squared per second. Now on top we have meters squared per second, on the bottom we have meters squared per second, so this is going to be a unitless quantity, which it should be because it's Reynolds number. So I get a Reynolds number of 1126. That is our Reynolds number. Okay. Now going back over here, we have our Reynolds number, and it's 1126, so it's going to fall somewhere in this range right here, which means we're going to use this formula. Our Nusselt number is 0.683 times the Reynolds number to this, to the 0.466, times the Prandtl number to the 1/3. Okay, so we need Prandtl number now, so let's get that next. Clear this. Alright. Now let's change colors just for fun. Okay, this one's good. Okay, so we need a Prandtl number. And for that, we are going to look it up in the tables as well. Alright. So, again, using our film temperature of 92 degrees, this leads to a Prandtl number. Prandtl number of 0.7128. That is our Prandtl number. And also note that I use the same film temperature in the same air property table, so this is also an interpolated value. Alright, so let's go back and grab our equation, which is over here, which is going to be this one. So let's go ahead and write that one down. So our Nusselt number for a cylinder is equal to 0.683 times the Reynolds number to 0.466 times the Prandtl number to the 1/3. Sorry, 1/3. There we go. Okay, so this is equal to 0.683. Our Reynolds number was 1126 to the 0.466. And our Prandtl number is right there, 0.7128. And this is, sorry. There you go. And this is to the 1/3. All right. Now I get a Nusselt number of 16.12. This is our Nusselt number. This is one of our answers. And something that you could do is you could go back to this equation and you could check it with this one and see if this one does indeed match what you get here. All right, let's move on. All right, so we have one of our answers. Now what we have to do is we need to find Q convection. We found Nusselt number, now we need to find Q convection. How are we going to do that? Let me change colors one more time, actually. Let's do that. Okay, so change colors. If you notice over here, we have our Nusselt number, we have our diameter, we don't have H, and we don't have K. If we had H, then we could use Newton's law of cooling, and then we can get our Q convection. So I think that's the direction I'm going to take this. But I need K first, and I can get K from the tables. And once I have K, I have everything else except H, and I would get my H. So let's go ahead and do that. So the first thing I need is K. So again, my film temperature is 92 degrees. And this is going to give you my thermal conductivity, which is 0.0304. This is watts per meter degrees Celsius. Okay, so this is our K value. And now let's write down that formula, which we had Nusselt number of cylinder is equal to HD on K, which is 16.12, that's our Nusselt number, is equal to H, which we don't know. Our diameter is 0.01 meters, and our K is 0.0304 watts per meter degrees Celsius. And this gives me an H of 49 watts per meter squared degrees Celsius. All right. Now that we have H, we can go ahead and use Newton's law of cooling to get our Q convection. Let's do that. And let's change colors one more time. Yeah, there we go. Let's do that. All right. So we need Q convection. And we're going to use Newton's law of cooling. So we have H times area of the surface times temperature of the surface minus temperature of the environment. Okay, so I think we have H, we have our area of surface, and we have all this. Yeah, we have all that, so we can go ahead and solve for our Q convection. Let's put in the numbers. So this is 49 watts per meter squared degrees Celsius. Area of the surface, this is pi dl, so this is pi times the diameter, which is 0.01 meters, and L, which is 0.07 meters. That was given at the beginning. Now, temperature of the surface is 158 degrees Celsius, and temperature of the environment is 26 degrees Celsius. I can't talk anymore. Okay. So now all this should give us our Q convection. All right. So let's go ahead and work that out. We get 14.22, and this is watts, because this is on the bottom, cancels out with both these meters. This is just Celsius, cancels out with this Celsius, and we get watts. This is our Q convection. Now, there's just one thing I want to point out. That, remember at the beginning that I said I put in, let me clear this, actually, no, this is fine. Okay, let's just use a different color. All right, remember at the beginning that I said I put in 12 volts and I had a current of 2.04 amps? Now if I multiply these two together, that should give me my power input. So let's do that. So we have 12 times 2.04, and this is 24.5 watts. Now this is weird because I'm putting in 24.5 watts, but my Q convection is only 14.22 watts. So I'm missing 10 watts here. What happened to those 10 watts? Because if you look back to our drawing, we had air, and we have a cylinder, and we have some kind of power input. Now, this is really hot, 158 degrees, and the air is at 26 degrees room temperature. And the air is flowing over the cylinder, so the heat should be being transferred over to the air. But it's not. Only 14.22 watts are being transferred over to the air. So what happened to my other 10 watts? And this is answered by Q radiation. Q radiation is the answer to this. The other 10 watts, well, there's also other things involved, like losses and things like that. But a lot of the other 10 watts are being lost to our Q radiation. And when you add up the Q radiation with our Q convection, you should get something pretty close to our input of, I can't circle this thing, there we go, 24.5 watts. Yeah, and I think that is it for this video, and I will see you on the next one.